All right, let's get started. So, I guess before we get started, I was going to make a couple comments regarding the homework, all right? As I mentioned before, the hope was to try and split this class into kind of two pots with respect to grades, right? A pot with which you get to earn that credit, most of which, at home. It's a non-assessment based, okay? That'd be your homework. So there's 50% of the classes there. And then 50% of the classes through assessments, like our quizzes, and then we're gonna have a final exam, okay? So with that being said, with homeworks being worth 50%, right, and there being 10 homeworks in this class, every homework is worth 5% of this class, right? And as engineers, right, calculations are our way in which we communicate with others, okay? So you need to be proud of the work that you're putting forward, okay? Check out the syllabus. There's a lot of description as to what is expected in a homework assignment. And Daruk has spent time, especially on the first homework assignment. Some of you probably got penalized a little bit for not using grid paper or not laying out the problem statement well enough, okay? I can't stress that enough, especially moving forward as you guys move through your careers here at I said Morrison, Maryland, that's where I used to work, okay? Montana State, okay? Being concise, neat, clear with your work will go a long ways, okay? Especially with partial credit, all right? Especially for me as a grader, if I see someone who has put at least some forethought and effort into just at least setting up the problem, I'm more liable to give them more points than someone that just sloppily writes something out, okay? Whether or not those two got the same answer, right? If they were wrong, I would probably give the person who at least formulated their thoughts and ideas in a better fashion and was more clear with them would get more credit than someone who just, say, printed off the assignment and then wrote the answers directly on the assignment paper, okay? So think about that. Late homeworks, all right? So homeworks are due at 5 p.m. And with that, right, if you are late with a homework assignment, it gets cut in half, right? So no longer are you able to get 5% of your final grade, you're only able to get 2.5% of your final grade. So try not to miss that either, okay? So with that being said, Thursday is homework 2 is due, that's tomorrow, right? 5 p.m., it's due to Gradescope, all right? The quiz for this week, which is all over the same similar material, is available today, if you'd like to start taking it today, through Friday, just like it was last week. And I'm gonna try and keep up that trend as we move forward, all right? Unless there's some class objectives to it, objections to it, okay? Like I'm open to opening it up more. I'd rather make it so you guys get it done before the weekend, okay? I procrastinate just as much as any of you guys do, all right? So, if it was due by Saturday, I'd probably be spending my time on Saturday doing it, and I'd rather force you guys not to do that. But if you would like, I can open it up from Wednesday to Saturday, right? All you have to do is set aside an hour of your day, right? You get an hour to take it. You guys kind of have an idea of the caliber of questions that I'm asking on those quizzes also now, so. But so far, I'm gonna just continue with Wednesday through Friday, yeah.
Are quiz 1 grades out yet?
They should be, yeah. It should be updated to D2L. I went out there and I moved it into the quiz section. Okay, so that should be out there. I think the average on the quiz was 86% or something like that. All right. So I think you guys did very well. As you can imagine, right, based on what you saw in the quizzes, it's more conceptual based than anything. Okay, and if I am asking you to calculate things, it's going to be fairly simple things, right? The homework assignment, there's like multi-steps to them, right? With the quiz questions, I'm trying to keep it limited this semester. I got a lot of feedback that it's tough because the quizzes, it's auto-graded, right? So partial credit kind of goes out the window. So I gotta be pretty particular in the questions that I ask, in which they've got to be concise, right? So that hopefully now I'm trying to pull that partial credit dispute out of it by just saying, okay, well, it's a one-step problem. You either get it or you don't get it, or conceptually, right, multi-question like A, B, C, or D, or true, false, or something like that, right? There's a right or a wrong, and you just get one chance at it. So, but yeah, did you check, and are those grades out there? Okay. Man, you guys are good, just checking in on the fly. All right. We're going to continue with axial systems. Oh, one last announcement, right? Next week, I will not be here, all right? I'm going to be posting lectures as I have been up to you on YouTube, right? Our YouTube channel. Go out to D2L. There's an announcement out there that I made at the beginning of the semester that gives you a link to the YouTube channel, all right? I'd suggest subscribing to it so you would get a notice that a new video is up. If not, that's fine too. But I will likely be just giving a 3-hour lecture or 3 1-hour lectures. I'll post them out there. I'll be available via email, okay? So reach out to me if you do have questions on homework, which I'm going to be issuing a homework tomorrow. That'll be due next Thursday. There'll be a quiz next week also, right? All over axial loads and things. So make sure that you stay in tune with what's going on in this class, right? Don't check out. I'm here. You can email me. We can set up a time on Teams if you'd like to discuss something, okay? The homework or the quizzes. Don't forget the EM Learning Center. Daruk, who's been grading your assignments, right? If there's an issue with grading, reach out to him. And you can copy me on that email if you'd like, or reach out to me and I'll go through Daruk. It doesn't matter. But if you have any questions on homework, reach out to myself or Daruk. Okay, you have Arash, who's in the EM Learning Center, and then you have Dr. Murray, right, Flynn. She's also there to help you guys as well. So a lot of resources. Don't feel bad about reaching out to any of us, okay, and we'll make it a point, okay? And then that following week is President's Day, right? So Monday, we don't have class, right? And there won't be a lecture that I'll post for that day, obviously. That's a straight holiday, okay? Any other questions? All right. Axial systems. On Monday, we went through determinate systems, right? Where we have, based on our free body diagram, we have as many or more equations of equilibrium as we do have unknowns. So we can actually calculate what those internal forces are, right? And we know in the end, we're looking for displacements. We went through and based on the principle of stress, right? Force over area, the principle of strain, change in length over the original length, and our modulus of elasticity, right? With respect to Hooke's law, which relates stress and strain with this idea of stiffness, right? This E value. We were able to get that equation, right? Our force deformation relationship. So now we're able to analyze axial systems, right? Rods, things that have axial forces in them, to determine what are our displacements, because as we know as designers, we're interested in not only strength, right, but also stiffness, which will give us displacements to make sure things are not only strong enough, but are actually usable, right? They meet our serviceability requirements. So in determinate systems, we have multi-segment rods, right? Almost a series of rods. They might be different materials. They might be different cross-sectional areas, right? But we are working through a rod system of multi-segments. Then we have overall rod systems. We talked about Romney Gym, okay, the walkway up above the gym over there, right, where we have, say, a walkway that's suspended by a system of rods. Okay, so then we have rod systems. We can then figure out our forces within our rods, right? Everything we need to know what our forces are. From there, we could figure out stresses. Maybe there's allowable stresses that we have for these rods, okay? Each of those, we could figure out displacements. Well, if our platform or walkway in this case was infinitely stiff, right? If we had a rigid bar here. If we figured out the displacements of rods 1 and 2, we would make a straight line between those two bars, right? So we could figure out the displacement anywhere along that bar, right? That was oriented at some angle now because we knew the displacements at the two ends of it. Or even if we didn't have the bar at the two ends, and maybe this bar cantilevered, maybe this bar continued off into space, right? We could figure out what that dimension was too, right? If we wanted to, using similar triangles, right? It's essentially just knowing the slope of a line. And so basically knowing our changes in geometry, we can figure out the displacement at anywhere along that member. So we went through an example with a multi-segment rod. We had a bronze rod and an aluminum rod. And we were looking at, well, what's the displacement of the joint between the two materials? And what's the displacement at the end of this rod that wasn't fixed, right? It was fixed at, say, a wall. And we were pulling on it, pulling on that rod away from the wall. We want to know, well, how far does this coupler move, or the coupling move between our two materials, and how far does the end of our rod move? And so we calculated that. Now we're going to run through an example where we're going to go through this rod system, right? So we went through a multi-segment. Now we're going to go through a rod system. So this would be like our Romney Gym platform, right? Where we'd have, say, a uniform load, American Society of Civil Engineers, specification 7, ASCE 7, okay, is one for civil engineers with which, and you CETs, when you get into, I think it's 412, we'll learn about ASCE 7, okay? And it's the governing code that gives us all of our loading in all of our buildings, okay? So what is our live load, right? If this is a classroom, do we put 40 pounds per square foot, assuming that is what all of us weigh in here at any given time, right? The corridor, if it's a first floor corridor, we're gonna put 100 pounds per square foot, right? Loading the first floor of Cobley Hall, APS, right? Any building on campus. If we're above the first floor and we're in a corridor, we're at 80 pounds per square foot, and so on and so forth, right? Live loads, dead loads, snow loads, flood loads, earth loads, okay, rain loads, all of those things are in that specification. And so that would be what would dictate this W, right? Give us this uniform load. If we were running a track, it would say, okay, if you have a suspended walkway, you have to put on there 60 pounds per square foot or something like that, right? They also have them in SI, which is this example problem is in SI, okay? In this case, they tell us that our rod length is 7 meters, okay? And each of these so L, 7 meters, okay? A dimension is 1.5 meters. B dimension is 3 meters, okay? One rod, rod 1 there, is made out of steel. Second rod is made out of aluminum. And each of these rods have different cross-sectional areas, as you can see. The steel rod is 175 millimeters squared. The aluminum rod is 300 millimeters squared. They give us this distributed load as 15 kilonewtons per meter. And they want us to determine the deflection of the rigid beam at point B. Right? Point B being right here. So they want us to figure out what is the deflection at point B. Well, if we go back to our solution process for multi-segment rods, right? If we're assuming that this is a rigid beam that's suspended between our two rods of varying material and cross-sectional area, right? In order to figure out the displacement of B, we're going to need to know the displacement at least 2 locations of this rigid beam, right? Once we knew the 2 location displacements, we essentially could make a straight line between them and we could figure out what the displacement is at B. In order to do that, we need to find displacements of rods 1 and 2. In order to find that, what do we need? That was a question to you guys. What's the first step? What did we do in the first step of the last problem?
Free body diagram.
Free body diagram. But the free body diagram would give us
Reaction.
reactions or forces, right, in our rod segments, which allow us to use our force deformation relationship. So let's start with our free body diagram. I'm going to give this free body diagram some coordinates so that I can put signs to my forces, right? We're going to have point A, point B, and point C in our free body diagram. I'm cutting off our rods on our free body diagram. So those rods now become forces. I'm going to assume that the force at A is upward, right? Or force in rod 1 is upward. I'm going to assume the force in rod 2 is also upward. We have another external force applied, right? The uniform load on this rigid beam. that uniform load on this rigid beam, as they mentioned, was 15 kilonewtons per meter. Well, we need to figure out a resultant, right? Remembering from statics, right? You would resolve this uniform load into a single acting load that acts at the centroid, right? So that we can then sum forces and sum moments. So I'm going to essentially exchange this uniform load for a single uniform force, right? That acts at the centroid of our uniform load, right? Which happens to be just at the center. If this was a linearly changing distributed load, right? If it started at 0 at B and went to some value at C, right? It would act at the centroid of that triangle, which would be 2/3 from the 0 point or 1/3 from the max magnitude. And that'd be our centroid. Could go out to the appendix that I posted on D2L or the appendix in the text and look up the centroid of a triangle. And the magnitude is just the area under that uniform load curve, right? So for the triangle, it's just the area of the triangle, 1/2 base times the height. In our case, it's just the height times the length, right? So we now have this force acting there, with which we know the magnitude is our length times the magnitude, or 45 kilonewtons, right? Making sure we consider units, right? They gave us the length of that uniform load in meters and the magnitude of the uniform load in kilonewtons per meter. The meters cancel out and we get kilonewtons. Well, we know the dimensions of everything, which we know is a component of our free body diagrams always. Make sure that we have those. Well, we know that our force acts at our centroid, right? The middle of our 3 meter length. That means we got 1.5 meters, 1.5 meters, and 1.5 meters. Well, we have 2 unknown forces, right? So I'm hoping to come up with 2 equations of equilibrium. What's one equation of equilibrium that we have?
Some moments.
Some moments. Where would you sum the moments about?
A.
Sweet. I'm glad you picked that because that's what I picked. All right, you can sum the moments about A equals 0. Why do we sum moments about A? Why did you decide to sum moments about A?
Is either A or C, and I like A.
You like A better?
Yeah.
Why did you like A better? I feel like both of them are the same, but there's a reason why you would pick A and C, right? Because you could pick B if you wanted to.
Oh,
right?
because it cancels,
One of the forces out, right? So if you pick an A, because the force at A has no moment arm, right? Our resulting equation of equilibrium is only going to have one of our unknown forces. So if we did sum of the moments about A equals 0, well, we're going to have force 2. It's going to be times a moment arm of 4.5 meters, right? Or 3 times 1.5. It's going to be positive because of the right-hand rule, right? F2 curls your fingers counterclockwise, thumbs pointing out of the screen. We get positive. Now we have the uniform force, or the uniform load force, which was 45 kilonewtons. And it has a moment arm of 3 meters. Well, we have one equation, one unknown. We can solve for F2. We're going to say it's 30 kilonewtons. What's the next equation of equilibrium we're going to use? We know what F2 is, right? Forces in the Y, exactly. Yes?
Just real quick,
Yeah.
on our homework for stuff like, just doing a moment problem like this,
Yeah.
you want us to write out our work, or can we just jump straight to the answer like that too?
I guess, what do you mean? How did I jump?
Well, do you want us to write, okay, multiply 45 by 3 and bring it over? And
I guess you wouldn't have to if you came up with the right answer, right? But I would recommend doing it so that, one, if you made a mistake here, right? One, you might be able to catch it. And two, if you made a mistake here and this becomes the wrong answer, Darut can say, okay, you made the mistake at this level, and then that's where it trickled through the entire thing, instead of just you writing down the wrong answer and he's not sure that you did this correctly. So I would recommend, in an effort of partial credit, to do that, okay? But if you feel real confident, you go for it, okay? So sum of the forces in the y equals 0, right? Well, we have F1 now. I assumed it's upward, so it's positive. We have 45 kilonewtons, it's downward. And we have 30 kilonewtons, that's upward. We just decided through F2. Well, that means F1 equals 15 kilonewtons. Right? Now, at this point, right, even if I didn't do any of this work, this is when I would sit back and say, all right, does this make sense? Right? If I was looking at this, and this was in the real world situation, and I had two rods, and I had a plank between them, and most of the load was on the C side, right, where F2 is, I'd assume F2 is going to be larger than F1, right? Can't imagine that I would be able to pick out exactly what the magnitudes were, but in general, I have an idea or a sense that F2 is going to be larger than F1. So I feel pretty good about it, okay? Okay. Was helping someone on a homework, right? Where I mentioned in class that the Poisson's ratio, right, is generally in that 0.2 to 0.3 range, right? 0.15 to 0.35. Right? But the answer that they were coming up with was a lot less than that. Right? And so if you would have been able to step back and looked at that and said, well, this doesn't really match what the range should be, okay? It's easy to come back after doing that and say, okay, something is messed up in this, right? And all it ended up being was there was a decimal point of a variable that came out of the problem statement, right? Where it was a tenth of what it should have been, okay? So things like that, always try and step back and look at this, okay? I know everyone wants to get this done, but it can help, okay? So we've come up with our forces, right? We want to figure out, we know the kind of the process here is forces, displacements, and then hopefully those displacements, and especially in a multi-segment, or not a multi-segment, but a rod system, we can then use those displacements to figure out the displacement of interest. So if we go back to our free body diagram, so now we have 15 kilonewtons and 30 kilonewtons. We have this resultant force equal to 45 kilonewtons. Some of the forces work out, some of the moments work out, equilibrium works out. Well, we're going to want to know what the displacement at rod 1 and rod 2 are, right? Because those are our displacements at point A and point C. We know that this force deformation relationship is this FL over AE, right? Hooke's law, stress and strain, all combined to one. So now we can just plug and chug through all of our forces, lengths, areas, which I think they gave it 175 millimeters squared. Well, what did I do here? Well, I know the force in rod 1 is 15 kilonewtons. Well, that's 15,000 newtons, right? Kilo is 1,000. We also know that that rod was 7 meters long. Well, I converted it to millimeters. Okay. I converted it to millimeters because they gave us the area in millimeters, 175 square millimeters. Then they also gave us, I think it was 200 gigapascals, right? And 1 gigapascal equals 1,000. We need one more zero there. megapascals. And 1 megapascal, as I mentioned earlier in this class, right, is 1 Newton per millimeter squared. So that 200 gigapascals that we had for steel became 200,000 megapascals. Well, I didn't really want to put megapascals into an equation that's just a function of newtons and millimeters. So I converted it to, or just essentially wrote it out as newtons per millimeter squared. In this case, all of the millimeters cancel but 1. The newtons cancel, and we end up with 3 millimeters as our displacement of rod 1. If I go through that same exercise of rod 2, now we have 30,000 newtons. We've got, they're both 7 meters long, or 7,000 millimeters. The aluminum rod is a little bit bigger in cross-sectional area. Now we have 300 millimeters squared. And 70,000 newtons per millimeter squared. So our aluminum rod, we find, displaced over 3 times that of our steel rod. Right? This one's kind of hard to get a sense of or a feel of because, right, there's a lot of moving pieces between these two. They might be the same length, which helps, but our load is double, right? But our cross-sectional area is larger, but our modulus of elasticity is smaller. So this one's a bit harder to step back and be like, okay, do I expect that the aluminum rod to displace more? Well, I wouldn't be able to tell, okay? So you gotta just feel confident in your numbers here, okay? So 3 millimeters and 10 millimeters. As mentioned, right, with rod systems, we have this system deformation that we need to look at in order to figure out what's the deformation at point B. That's our point in question. Well, originally our rigid bar was flat. After loading, we're going to get some deformation at A, and we know some deformation at B. So we're going to get this new geometry, right? New displaced shape for our bar. So we got 3 millimeters. Whoops. 3 millimeters. 10 millimeters. We know this distance is 4.5 millimeters, or meters, sorry. And we really want to know, right, when B displaced, how far did it displace? Well, now that we have this nice diagram, we can kind of dissect it a little bit, right? Well, if we look at this, looking at the displaced shape, well, B at least is deflecting the 3 millimeters, right? So if we separate this shape into essentially 2 different triangles, or 2 different shapes, sorry, a triangle and a rectangle, we kind of have two deformations, right? We have deformation 1 and deformation 2. Well, deformation 1 is 3 millimeters. Well, deformation 2 is going to be some slope, right, of that triangle. Whoops. Times the distance to B, right? Slope equals the rise over the run, right? So if we multiply that slope by the run, we should be able to get the rise. Well over 4.5 meters, right? That would be our total run. It rises 7 millimeters, right? It's going to be 10 millimeters minus 3 millimeters. So we know that B is 1 plus 2. Well, that's the same as saying 3 millimeters plus the slope now, right, is 7 millimeters. Over the run, which is 4.5 meters. Times the distance to B, well, that's 1.5 meters. Right, that'll give us what delta 2 is. The units work out here, right, because we're dividing by meters, but then I'm multiplying by meters. So these guys cancel out. We get millimeters plus millimeters. And we end up with a displacement at B equal to 5.33 millimeters. Question?
Yeah, can you go through the slope times the distance again? How are we getting that roughly?
Yeah, so we're using this as a triangle, right? Where we know 2 points on this triangle. It's essentially a line, like you would put 2 lines on a graph, right? We know 2 points of those, right? We can figure out the slope just like we figured out the modulus of elasticity. So the slope of this line is the rise over the run, right? In our case, the rise is downward, but same principle. So what we figured out for our slope, right? The slope of that line would be our rise, which is 7 millimeters, right? It dropped 7 millimeters. And the run is the distance in which it took to drop to 7 millimeters, right? So we essentially find the 2 legs of our triangle, the length of our triangle, and the height of our triangle. And that'll give us the slope, right? Of our triangle, that line. Knowing the slope of that line, we essentially are knowing what the rise is per run, right? So for every meter distance, we are going to drop a certain amount, okay? So that's what the slope it gave us is what is that drop of this line per a specified distance. In this case, it's 7 millimeters over 4.5 meters. And then if I multiply that by how far did I go, right? 1.5 meters, that's going to give us this drop of 7 millimeters. Does that help?
So we're basically similar triangles.
Yep, is exactly it. Yep. Yep. You could say that it's, right, this being, if you took that triangle, whoops, it's not the right triangle, to that triangle, right, you really get 7 millimeters to 4.5 millimeters is the same as x millimeters, right? That'd be the drop, or delta 2, right? This is delta 2, over 1.5 meters, right? That would be similar triangles. So we want delta 2. Well, delta 2 would be this equality multiplied by the length, or 1.5. So that's what this is. Any other questions? All right, now we're going to add a little complexity to it, okay? Determinate systems are easy, all right, comparatively to indeterminate systems. Just in the fact that we're just going to add another layer in that we need to essentially develop more equations, right? Indeterminate means we have more unknowns than equations of equilibrium. An example of which would be, whoops, what am I doing here? If we had a rod system that looked something like this, where it was a rod that was pinned at both ends, right? So we got no moment at the ends here. But then we have our fixed supports, right, that keep our rod from displacing vertically and horizontally. And then we ended up putting this force on it. our free body diagram would end up looking like this, where we would have force in the x at A, force in the x, or sorry, the y at A, force in the x at C, and force in the y at C. Make sure we have coordinates here, x, y. And then we'd have some sort of force in the x at B, right? There'd be a component of that force in each of our two directions. Force in the y at B, and that would be our free body diagram, right? We might know the force. We might know these two, right? If we knew these two, we have 4 unknowns, right? Horizontal force at A and C, and the vertical force at A and C. So we have 4 unknowns. And we really only have 3 equations of equilibrium, right? Right, we have some of the forces in the x and the y, and we have some of the moments, right? You could pick one location on this bar, we would sum the moments, we'd get an equation, we'd sum the forces in the x and y, right? So we'd have 3 equations. Well, we have 4 unknowns. We could not solve for that, right? We couldn't figure out all of those forces. What we call this, therefore, this is what we would call indeterminate to the first degree. Right? We have 1 additional unknown than we have equations of equilibrium. Right? If we had 5 unknowns, it'd be to the second degree. Another one here is, I want to make it out of black. Right, if we had a fixed rod, right? Fixed on both ends. It can't translate, right? It can't move up, can't move to the side. It can't rotate at either of these points. Well, if it can't rotate or translate, we end up with force in the x. We could call this point C, this point B, and this point A, right? Force in the x, force in the y, and we're going to have some sort of moment at C also, right? It's going to restrain that rotation. Same with A, right? Force in the x at A, force in the y at A, and we would have some moment at A. Well, now we're really in trouble, right? We've got 6 unknowns. We only have 3 equations of equilibrium. So what degree of indeterminacy is this? Third, yep. Right. So if I gave you a problem, it had forces on it, right? Some sort of setup or system. I could ask you if it's determinate or indeterminate. And if it was indeterminate, I could ask you what degree indeterminacy is this system, right? And you could tell me. And it's just based on your unknowns versus the equations of equilibrium that we have, right? Our 3 equations of equilibrium. well, we don't just give up here, right? There's a way to solve this, as I mentioned. So we might be lost, or we might be lost in the amount of equations that we have, right? But we can come up with additional equations. So in the solution process, same as the determinant, what was the first step we did in all of our other examples? Free body diagram, yeah. You're gonna get sick of that, but that's fine. Free body diagram, right? Always gonna start with that. We need internal forces. That free body diagram will allow us to find expressions for right, some of the forces in the X, some of the forces in the Y, right? Some of the moments. We were living in the three-dimensional world in this class. Let's say some of the forces in the Z, right? Once we have these expressions, we can determine, okay, well, are we indeterminate to the first degree, second degree, third degree, right? In this class, we'll be focusing mainly on the first degree. Our next step is coming up with a relationship of deformations, right? We have this equation, our force deformation equation, that gives us what's the deformation based on force, length, cross-sectional area, right, and stiffness, right? What are our material properties? And so if we knew, like in our rod system, if we knew that, right, this is determinate, but the second we add a third rod in this, it's indeterminate, right? So we're going to have 3 unknowns and only 2 equations of equilibrium. But if we put a third rod in here, right, we could figure out a relationship based on similar triangles that relates to deformation of rod 2 or rod, if there was a rod at B, for instance. Right? We could figure out a relationship that relates the deformation of rod B to rod A and rod C. Well, therein lies another equation in which we can use to solve for unknown forces. So that's what we end up doing, is we figure out or determine how the system will deform. And the whole reason for this is we need more equations. We're stuck, right? We have 3 equations of equilibrium. We have more unknowns. So we need to go through and say, okay, well, now that we know that the force, right, relates to deformation, if we came up with a relationship that says the displacement in rod 1 is half of the displacement in rod 2, well, we could sub in our FL over AE equations for each of our deformations, and then we have an additional equation, right? So how does this work in axial systems? Well, there's a few different types of axial systems, and each of those axial systems have different behaviors. Well, if we start with our rod system like we just looked at, we could look at angular relationships. Right? Just as I mentioned, if we had a series of rods, call this rod 1, 2, 3, and 4, and they were all holding up a rigid bar, and we loaded that rigid bar somehow, whether it was with a point load, uniform load, or combination thereof, right? We might get some sort of displacement, like that, something like that. where we could then come up with a relationship and say that rod 2 elongates could come up with a relationship that determined that rod 2 elongates proportional to rod 3, right? Or rod 3 proportional to rod 1, right? We had this similar triangle thing figured out, right? Or 2 to 4. So we can come up with an angular relationship. Some of our rod systems are a bit simpler. We might have something where we have, say, a material 1 and a material 2. And they are working together, right, side by side, or what we might call in parallel, right, between a fixed support and some plate or something that moves, right? And when it moves, we know that both of those materials move together, right? And if both of those materials move together, we could say the deformation of 1 equals the deformation of 2, right? Or the deformation of all members is equal. So when it deforms, say we added force to this end, right? Or we'll talk in a little bit, maybe we raise the temperature of this, right? So that this plate moves, and they're gonna have to move together, right? Because they're connected. We've got a last one we'll talk about is our total deformation in some systems. Can be equal to zero. What does that look like? Well, we can have a system, or what we used to call a multi-segment rod system, where we have, say, rod 1 and rod 2, and say we add some sort of force P at the coupler between these two materials, right? And it's fixed at both ends. Well, we know at that point then that if it's fixed at both ends, our total displacement has to equal 0, right? We have fixed plates at both ends, they're not moving. Or we would say that the deformation of 1 plus the deformation of 2 equals 0. Might call this in series, right? From one to the next. We have fixed supports. So if we push that plate over, right? If rod 1 elongates by 1 millimeter, well, rod 2 has to get shorter by 1 millimeter, right? And lastly, we'll just write this. Right? From after we determine how the system will deform, well, we have our force deformation. We can relate forces now, which is our unknowns. We can relate that to deformation. We've already done that. That's our delta is force length over area times modulus of elasticity, right? And I'm running out of room, and I ran out of time. So I will see you all on Friday. Don't forget, homework, 5 p.m. tomorrow. Quiz is out there on D2L. Don't forget that also. It's due by midnight on Friday. Okay, it is available if you want to start it now. If you want to wait, Daruk should put out the solution to the homework on Friday morning, by Friday morning. so that you would have that if you wanted to have that while taking the quiz.